Group 5 were tasked with designing and manufacturing a robot to compete in the modified version of the F180 RoboCup Small Size League tournament. The competition came into existence in order to allow small teams of engineers from all over the world compete against each other in the hope it would aid in completing the goal of having a team of fully autonomous humanoid robots win a game of soccer against the best human soccer teams in the world by the year 2050. The robot's individual subsystems were broken down into 4 main categories. Vision, headed up by Max Murphy. Artificial intelligence, managed by James Barker. The robot's drive system, implemented by Riley Johnston, and its kicker and dribbler mechanisms, designed and integrated by Shenas Google. The robot's competition environment consists of a purpose-built, square-shaped soccer field with a 2x2 meter area. The robot itself must have a maximum diameter of 180 millimeters, a maximum height of 225 millimeters, and a predominantly black exterior. Additionally, when viewed from above, the robot must not cover more than 20% of the ball's cross-sectional area. The robot must be able to consistently move towards and kick a goal at a rate of 2 goals per minute, while successfully avoiding multiple obstacles.
The chosen design for our project was a 3-wheeled omni-drive system with a 120-degree offset powered by 6-volt DC motors. Our design implemented an open-loop controller utilising PWM signals calculated using the kinematic equations for each motor. To minimise costs, our team chose to 3D print our wheels. The wheel design consisted of 2 sections at a 50mm diameter, with 16 rollers offset at 45 degrees to ensure that there was always a roller in contact with the ground. Each roller was wrapped in shrink wrap to increase friction and minimise the possibility of skidding during motion. To determine the desired motion, the drive system received a desired heading and speed, which was converted into linear and rotational velocities that fed into the program. The drive system then computed these velocities to calculate a duty cycle for each motor. These duty cycles were converted into PWM signals that went through the motor driver circuit and buck converter to ensure maximum current and delivery to the motors. Our drivetrain design was capable of holonomic movement with 3 degrees of freedom and provided the robot with all necessary movements for navigation towards the ball while also being capable of avoiding obstacles without excessive changes to the heading.
In order to allow the robot to be able to keep the ball close when moving, a dribbler system had to be designed and implemented. The dribbler consisted of a spinning cylinder that would exert a downward force onto the ball, causing it to spin backwards into the robot, allowing the bot to reverse and turn whilst maintaining possession. The dribbler's final design was a simple split-cylinder shape, coated in a grip tape similar to that used on tennis racket handles. The dribbler was actuated using a medium torque motor with a belt drive system. Once the robot had possession of the ball and the intended goal was within the appropriate field of vision, the soccer bot needed to be able to kick the ball with enough force to score a goal. The kicker's overall design need only consist of a solenoid actuator connected to a 3D printed kicker arm that extended out and underneath the robot's dribbler. Ultimately, the kicker and dribbler would be controlled by both the robot's vision system and its artificial intelligence.
The vision system was needed so the robot could find and identify the ball, the obstacles, the balls, and the goals. When doing this, the vision system had to have no more than 2 false negatives. This is when an object is in the robot's field of view, but it does not identify it. For identified objects, vision had to provide AI with their range and bearing, and do this at a speed of approximately 15 to 20 frames per second, so it was fast enough to keep up with the robot's movement. The ball, ground, and goals were identified using color. The image captured was converted to a LAB color space and then segmented. The obstacles were segmented using intensity, finding dark areas of the image. The binary image of each object was processed using opening and closing. This removed noise. Contours were then found in each binary image. A contour is a consistent line that bounds a group of pixels. Contours that were too small were removed before their width and position on the screen was used to calculate object range and bearing.
For our navigation system, we utilised an artificial potential field method. This is a reactive navigation method which continuously generates both a goal and obstacle map from the vision data. For this method to operate, the system receives a distance and bearing to the goal and each obstacle from the viewing field. Each map is based on the local polar coordinates of the robot from 0 to 360 degrees. The goal map generates an attractive force, or angle at which the robot should turn towards, based on the position of the goal. The navigation system relies on 2 separate states, a search state and a seeking state. During the seeking state, the ball is recognized as being seen, and the program will continuously update the potential field. In the search state, the robot will use its Omni drive system to rotate until it finds its goal.